This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, let's get started so we can use our time well. All right, so what we're going to look at, just for a few more slides basically, is sort of rounding out our conversation about smooth muscle. And remember, contextually, very, very, very slow contractions because they are very, very slow functions. So we can be smarter about the way we do this. We can be a lot more economical. And that's really consistent with the fact that we want to, for example, constrict a blood vessel and maintain that tone for often hours. You know, when we're resting, we tend to perfuse our vascular beds fairly constantly, and that is regulated by a level of constant force in the smooth muscles in those arterioles. Now, you don't want to be churning over ATP, doing that every cross-bridge cycle, etc. You want to actually have a system where that cycle is much slower, plus you can also attach and stay attached for a little bit longer. Because remember, it's that attachment between myosin and actin, which is at the heart of length changes, so moving position, but also generating force through that attachment. So if we can prolong that state, then, and therefore slow down that state, our utilisation of ATP is significantly reduced. So how do we do that? Well, we've got small cells, so constant or similar to cardiac cells. We can draw calcium down its gradient into the cell through voltage-sensitive calcium channels. We can trigger additional release from the SR, so very similar to cardiac cells. This is really poorly developed in smooth muscle, so it's really even more dependent on its external supply. But again, it's on that far end of the spectrum of need for speed. Here, this calcium has got to do something a little bit differently because the actin and myosin are not ready to bind together. It's not like they're being kept apart like they are for cardiac and skeletal. They're just not fit for purpose. They've got to be modified. And the thing that is modified is that myosin itself, that the head of the myosin molecule would not fit onto the actin binding site without being phosphorylated. All right, so in the absence of phosphorylation, then you don't get interaction between actin and myosin. So we've got to modify it. How do we do that? Well, to phosphorylate, we need a phosphorylase. So a kinase, and of course we'll use a phosphorylase to turn the system off. But we need a kinase, and most kinases are very creatively named after the things they do or their targets. In this case, a myosin light chain kinase means that you're phosphorylating the myosin light chain, a little head region on that myosin molecule. How do we turn that enzyme on? Well, it's an enzyme that's activated by binding calmodulin, which is a very common trigger molecule in cell biology. It is only activated itself by binding calcium. So there are binding sites on calmodulin. It has a lot of structural homology with troponin, calmodulin. So you can sort of think of it like a mobile troponin. So this is like your intracellular sensor that the cell's activated. Right? The thing that's telling the cell that calcium is increased is the consequential elevation of this signalling molecule, this receptor, molecular sensor. So let's go back up to the top. Calcium in, elevated, binding to calmodulin. The calmodulin able to activate an enzyme, which is a kinase. The kinase working on its specificity to phosphorylate the heads of myosin. Myosin now just hunts out actin and creates bonds that generate force. Now, I've mentioned also that these filaments are not highly organised. The time taken here and this phosphorylation also encourages the formation of thick filaments. So we start to get more structural certainty that comes after activation. So this is pretty straightforward. It tells you both that they're not striated because they're not highly organised to start, that time's not an issue, so we can undergo a whole bunch of biochemical steps, etc. And that if we can do this to activate, then we can just undo it to relax those muscle cells. So how do you reverse the cycle? Well, sorry, this little insert I didn't mention, I mentioned verbally, but this is that sort of arrangement and formation of more organised filaments that I talked about but didn't use the slide to interact with. So if you just intersperse that on my little verbiage of a couple of minutes ago, shows you that activity taking these individual molecules to reorganise or increase the organisation of thick filaments. Right, so how do we reverse it? Relaxation then becomes an undoing of this. We use something that gets rid of the phosphates. And once you've got phosphates removed through a phosphatase, then these guys are no longer able to interact, actin and myosin. And clearly, the relaxation is triggered by just not allowing calcium to enter anymore, so turning off the entry, but also taking up the calcium that has been released. And of course, against the gradient, so using a calcium pump, a sarcoplasmic reticulum calcium pump or a SERCA, and these are present in all muscle cell types. And of course, because it's not just come from inside, it's come from outside, we pump out through a sodium-calcium exchanger. So a lot of recurrent elements here. Now, the variance can come from the fact that this phosphatase can act when the myosin is not bound to actin, so that it's got phosphate on it, and it's not bound to actin, right? And that will mean that that modified myosin, the one without the phosphate, is no longer able to do cross-bridge cycling. But it can also act when that myosin is attached to actin, all right? The phosphatase is not fussy. It's just going to look for that phosphate group and cut it off. If it does it when it's attached to myosin to actin, it actually sort of locks that state in for a longer period of time. All right? So it creates a state called latch, which is a longer lasting attachment, which is how smooth muscle has this enhanced ability to maintain force for longer periods of time. Now, what it can't do is change length, though. If you think about it, the attachment locks it in. How does muscle change length? Well, it detaches, attaches somewhere else, moves along, and does that cycling. That's how you get length changes. If you're locked in place, then you sort of forego that ability to shorten, but you keep the ability to generate force. So it becomes an efficient holding mechanism, but not a velocity generating or shortening mechanism. And that's what's described sort of theoretically here, that you can have these longer attachment cycles. And remember, attachment, detachment in skeletal muscle all requires ATP as part of each cycle, each one of these, in every cross bridge, in every filament, in every muscle fibre, of every motor unit. It's a lot of turnover of ATP. The longer cycles here for smooth muscle means that it can maintain force of comparable outcomes, but it's always going to compromise its ability to shorten, all right? Because that's just not what we want smooth muscle to do. And if it's going to do that, it's going to do it slowly in changing tone or slowly in propelling food, for example. Doesn't need to be done microsecond timescale. It's a much slower process. So that sort of phosphorylation or comparison between this more phasic or faster turnover of cross bridges and more tonic, prolonged force that happens in smooth muscle is sort of coupled here with this measure of phosphorylation. And you can see here as we increase it and decrease it, of course we have an impact on the force by decreasing the phosphorylation, or dephosphorylation is the thing that's turning off the force, but we're reducing phosphorylation per se. If we do some of that dephosphorylation while the cross bridges are attached, we sort of maintain this level of force and also phosphorylation level. So they're coupled and allow us to sort of distinguish between this phasic shortening behaviour and this longer-term maintained behaviour. Now we'll come back to touch on some of those elements progressively. So this last diagram really just does a bit of a side-by-side comparison. That there are some similarities, even in the extremes. And remember, we've sort of got cardiac muscle tucked here in the middle between our extremes. Cardiac's got a lot of the properties of skeletal, the structural organisation, the cross-bridge cycle, very much the same. Action potential's comparable but not identical. But it also has, cardiac muscle, a lot of the properties of smooth muscle in that it's got a reduced time frame, etc. It's got a dependence on the influx of calcium from the external environment that wasn't evident in skeletal muscle. Clearly, the extremes suggest that this is an inherent capacity of skeletal muscle, that they're fit for purpose, the actin and myosin. Here we need a whole bunch of biochemical events to get them ready to interact to generate force. Right, so for us, a lot of what we're going to do is start to put things together within the system itself. And we can see that where do we put these various muscle types? Well, we know cardiac muscle sits wholly in here, and both nodal and contractile elements of it. And that around the great vessels and the more minor vessels, so we break them into arteries, arterioles, capillaries, venules and veins, largely based on size, we can see that when we look for smooth muscle, it's not everywhere, right? It's not present in the capillaries. You should know why it's not present in capillaries. Anyone got an idea about why you wouldn't put smooth muscle in capillaries? Be confident. Why? What's capillary? What's the point of having capillaries? Exchange. And we've learned a lot about exchange, that you want big surface area, very thin. Right? You do not want to pack smooth muscle in there. If you want to control stuff getting to those capillary beds, you do all that control beforehand. So you're looking here that there's a logic to this distribution, that a lot of the gatekeeper function about whether a capillary bed is perfused or not is undertaken by the arteriole itself, that is just before that element of the capillary bed. So this becomes fairly straightforward, just in terms of its logic. Now we know the overall reasons for having a capillary system is that we need coordinated function, we need the ability to distribute nutrients and gases to all tissues. We know that the cardiovascular system is very close to, has tendrils, capillary beds that are close to every cell in the body. So we just need to coordinate the overall function and whether we turn off a bed or not based on how we control those smooth muscle gatekeepers. We know that some coordinated functions come through circulating factors. So the hormonal system we've already expressed as being release it into the cardiovascular system and allow only those cells that have got receptors to respond to that. That's efficient for some control mechanisms, not for others. We know cardiovascular system also, because it takes away wastes, needs to communicate with the external environment, both for gas exchange, but also for heat exchange, very important part of thermoregulation as well. So what we're going to look at is a range of properties both about the capillary beds, and here a lot of this is, you've just touched on some of it, what's the logic of the movement of molecules in capillary beds? It's just like Fick's law again, but in a system, right? And you go, Fick's law, not again, how many times have we done that? But the principles are exactly the same, right? If you know them, you'll breeze through this. If you don't, it's a great refresher. So, because when we get down to pumping blood in this very simple diagram of a cardiovascular system, with the capillaries as the site of exchange with cells around them, then gradients are going to be important for movement of fluids, movement of gases, and also metabolites. So these are going to be key elements about movement here. So we'll try and move through that fairly quickly. Stephen Harrop will talk to you about the renal system, so the removal of sort of gross levels of excess metabolites or byproducts, etc. And there the control of blood flow through the renal capillaries is critical as well. So we'll try and lay a little bit of foundation for what he'll pick up with you a little bit later as well. All right, so flow. Does anyone have nightmares when they think about physics for biomedicine? All right. Did Michelle do the lectures with you last year? Michelle Livett, was it? Physics. I'm just trying to remember who it was last year. Quick refresher. We'll do these very quickly. So if you've got your devices out, please discuss, because I'd like you to remind each other rather than me have to remind you about the impacts. The scenarios here, remember me, I'm the guy who always says there's missing information, I'm going to trick you. In this case, all these things are exactly the same, no missing information, so trust me. The only things that are different are these pressure values on either side of the equations. So which one will have the highest rate of flow? You should be discussing with your neighbour what flow is. What does he mean by flow? Because how can you answer a question without understanding the question?
I'm going to say C.
Yeah.
Biggest pressure difference.
How's your math? What about A? So it comes down to not just grading. So, all right. Show results. All right. You know what the right answers are? A or C. So this is not about gradients or magnitudes of denominators and stuff. It's about pressure difference. So A or C, all right? The usual confounder can be, oh, there's higher pressures for option D. High pressures are only part of it. You need a pressure difference between two regions to get movement, all right? The magnitude of that difference is what determines the rate of flow. And it becomes really important in terms of feeding capillary beds, etc. Because, you know, we regulate blood pressure. We do that for a reason. Right. So flow is proportional to that the difference in pressure between those. There's your take-home message. Right, here, setting the question up. These two tubes, 2 and 4, are the same length. This one has greater diameter, but that diameter is the same as this one. I'm trying to give you the missing variables before you go. I don't trust him again. This one's got the same diameter as this one, but it's a shorter length. Again, what is the answer? And I've summarised that as sort of mid-length and thin versus long and wide, but here's your representation. What do you reckon?
Fully law.
What?
The fully law.
Yeah, it's coming up. Oh, and in case your mouse, the pressure difference is the same for all of those, all right? That's a constant. Just checking, because some people get a calculator out and just make sure I'm checking. Right, drum roll, show results. 75% short and wide is a good thing. Absolutely good thing. Because again, it becomes about resistance. We want minimal interaction. If we're flowing down a vessel, I don't want to be bumping into walls and having friction slow me down. The less of that I get, the better. So a shorter journey, great. A wider pathway, great. All right? Given all the other things are constant. So we're just sort of building our cardiovascular system a little bit here. Right, so length affects resistance through friction, and diameter contributes to that clearly, as we've already seen. Right, who's thirsty? Where's flow highest? And just in case, the straws, although different colours, are exactly the same. The person sucking on the end of them is applying exactly the same amount of pressure. All right? All constants. Go to it. But I just said they're applying the same amount of pressure. Because it's a fair thing. Well, who's sucking on it, is it?
So,
Yeah.
it's why people with distended tummy and high blood pressure.
Yeah, because it's vascularised. Yeah. Alrighty, show the results. Oh. I actually like thick. Who likes thick shakes more than milkshakes? I'm with it. Yeah. Something about get more bang for your buck or something, more pleasing. Clearly, viscosity here is a significant factor. Again, it's about how many particles in that vessel, and therefore how likely there are to be interactions, etc. So thin is good, thin in terms of viscosity, I mean. So fluid viscosity affects resistance, and again it's related to friction. Now I'm going to put them together. Now we're going to put them into a cardiovascular system, because we have to control these sorts of things, and we have to think about flow within that system. So of these three variables we've talked about, which one is the most practical? Now, I'd be going, what does he mean by practical? All right, but that's up to you to discuss that. So what do I mean by practical? I'm just reinforcing my reputation as... What do you reckon, Yossi? When in doubt, go with C. I like your logic. Let's go with C. Well done. All right, so the reason here that we have smooth muscle, as we just talked about, around those vessels is to work on width or diameter, constriction, etc., etc. There is, of course, some logic if you think the other things are relevant but not easily controlled. Clearly, if we send blood through a more tortuous pathway, it's going to affect its flow. So if you have beds open and it's got to follow along the pathway. Blood viscosity comes into it when you think about blood thinners and also EPO, so increasing your red blood count if you're an athlete looking for an O2 carrying advantage, etc. The downside of that is the increase in viscosity of the blood that you now have with all that extra red blood cell number in it. So these are all related to function, but the body controls the width of vessels, etc. And it does that by just playing with diameter, and it's a description called, would you like to say it, Yossi? What's it called? Pasolini's law, all right. Does anybody know French? Is that a good description? Come on, who's doing French as breads? Someone's got to be doing it. All right, we won't argue that one about. Well, anyway, that relationship says if we get rid of all these constants, because we've got resistance to flow, is proportional to length, viscosity, and 1 over the radius. If we get rid of things that we think are constant in a particular vascular bed, that we get the resistance being proportional to the radius, to the power of 4. So it's a huge valve for controlling flow, i.e. controlling resistance in that vessel. So it's a thing the body does. So if we're talking about flow through the system and directing that, we can turn things off with or moderate that rate of flow through that local bed by very small changes in the diameter. Right. Now, we talked about tone a little bit, and I alluded to that latch state. Remember, we just talked about it, that if you phosphorylate a myosin head in smooth muscle and it attaches, it's the only way it can attach is to be phosphorylated. If you're a phosphorylase and you clip that phosphate off and it's stuck in there, you're in a latch state, a long-lasting contractile state or force-generating state, but not shortening state. Now, a lot of the tone in vessels is contributed by these longer-lasting, more efficient states of myosin. But it's not all myosin heads, because it is a serendipity. You know, the enzyme itself is not selective. Some it will clip while they're attached, some it will clip while they're free. But we have this ability to make adjustments about tone. Now you think, do we want to have that neuronally controlled? So every bed is monitored neuronally and go, what's happening there? Do I tweak this valve and let blood in or out? Do I need that level of coordination? Or can I trust a little bit that the beds themselves, the vascular beds where the capillaries are, can determine their rate of flow a little bit independently? Right. The independence makes sense when you think that the body is pretty complex and maybe different areas are undergoing different activity levels, different functions, different motor patterns, different types of exercise, etc., different metabolism. So a lot of that control is local. And if you look on the right-hand side of this diagram, you'll see that the two states we want to control are the level of constriction or dilation. So we talk about vasoconstriction, tightening, reducing the diameter, or dilating it, opening it up. And they're fairly straightforward words. Now, if you look at the list of factors where the local control can change that level of contraction, you'll see that there are some common factors in there, right? There's O2 levels and carbon dioxide metabolites. There's some neurotransmitters or some hormones. Remember, a neurotransmitter can be a hormone. As soon as you put it in the cardiovascular system, it's by definition a hormone, not a neurotransmitter. Some of those will be really important in controlling blood flow through the kidneys. So something like vasopressin, angiotensin II, you will come back to learn more about with Stephen Harrop in the renal block. All right, so we won't touch on those too much now. But you need to remember this is the sort of effect they're having. They're being released within the body in the cardiovascular system. You've got receptors in those arteries or arterioles down at that level controlling blood flow into those kidneys, that these hormones are tweaking that blood flow based on water balance constraints of the body. That's the context. For us, a couple of key things here. If this capillary bed is in an actively contracting muscle, right, it's going to be consuming oxygen, building up metabolites or depleting metabolites but increasing byproducts, and it's going to be producing carbon dioxide. What sensible signals to have to say to that blood vessel that I need a bit more blood? Bring down some blood with some new oxygen and take away my excess carbon dioxide. Give me some more metabolites. There's an inherent logic in doing that. And if you flip the ups and down arrows on the right-hand side, you can see you can flip between dilation and constriction based on whether they're up or down. Right? So those things should be pretty obvious to you. This is about metabolism in a bed that might be doing something, producing something, consuming something, and its own signals will help control the flow of blood to that local area. The thing that probably is less obvious is the fact that myogenic activity can do that as well. So if you think about what we're talking about is very fragile, thin beds of tissue where you want this exchange, underpinning Fick's law, nice big surface area, very thin layers, gradients, etc. And the only way we can protect that is by making sure there's not too much blood rushing into that area, blowing it apart. Now that potentially could happen every time you go from a lying position to a standing position, and gravity says, send a lot of blood down to the floor, to my feet. All right? Gravity will do that in its own right. It'll take blood away from your head, move it to your feet, just the effect of gravity. So how do we control that? Well, we have some stretch sensitivity in those arterial beds that say blood is on its way, we better constrain that. So what do you think a negative feedback loop would do when blood goes down and stretches smooth muscle? What's the obvious thing you're going to say to me? It's going to contract. Right? So an increased stretch will, by negative feedback, cause contraction, i.e. constriction, i.e. a dampening on the blood that's going to enter that capillary bed. Right? So that's just putting a lot of very simple principles together. Now that is called the myogenic. You're assuming a position where you're going to say something, I can tell it. You've got your arms crossed as well.
No, okay, I won't. I'll uncross my arm. So David mentioned that when we stand up and gravity draws blood to our feet, so we have this myogenic reflex, which is the stretch on the vessel wall causes constriction, but we also have the opposite effect above the heart. So when we stand up on our feet, we lose blood flow going to the head, which which decreases pressure inside the vessel, which causes those vessels to dilate, thus therefore increasing flow to the brain, which is only a static reflex there as well.
Perfect. Right, so something's got to sense it. All right, and we've talked about different classes of channels before. We've talked about, what do we got? Ligand-gated channels, pretty comfortable with those, neurotransmitter based, etc. We've got voltage-sensitive channels. We talked about sensory stuff a little bit by saying there are some nerve endings that may get squished and contracted. Remember our spindles are one of those sorts of things? Well, smooth muscle has this similar class of channels that are stretch sensitive. So all you need, if you think about, well, how do I get smooth muscle to contract? I already know, I increase calcium. And we'll go through that cascade, I'm not going to say it again. So how do I do that? They're channels that are voltage sensitive, so that they're voltage sensitive, they're not stretch sensitive. So I need something else that's stretch sensitive, that's going to depolarise that cell. So put together the elements you're missing here. So all I need to add to the system is something that's a stretch sensitive channel. Remember, by that I mean its change in tertiary structure is not caused by a change in electric field or a ligand binding to a particular site, but it is some physical contortion that opens or gates open that structure. And if you add that to the mix, then there's been a number of different channel types that fit that bill that are called epithelial sodium channels or transient receptor potential channels, TRIPS. And in your biomedical evolution, you'll come across lots of different types of TRIP channels in various pathologies, physiologies, biochemical cascades, etc. So I'm not going to worry about, I'd never give you this acronym without explaining what it is. I don't expect you to remember it per se. Just be comfortable when you hear it, because there are so many variants. And the reason I'm saying that is because here's a TRIP-M versus a TRIP-C. And there's a number after it. When you see a number after it, that means there's more than one of them. So there's a huge repository of these. I don't want you to know them. I just want you to know there's a class of channels, the ENaCs, epithelial sodium channels, and the TRIPS, that if you look at their net effect here, when we've got pressure or stretch, they allow movement of sodium or calcium into the cell, depolarising the cell, opening voltage-sensitive calcium channels, and the rest down the middle is exactly what we just talked about. Okay? So it just becomes a bit of a sensor, a stretch sensor that's not neuronal, it's just a channel type that's stretch activated. Now, the amount of depolarisation can vary in the head versus the feet. It's just a way of titrating up the level of contractility feeding those capillary beds, so in those arterioles. All right, so just putting together little pieces of the same sort of information. Now, I haven't got a question underneath this, but I want you to start to think about something about pressure. And we want to get in your head a little bit here that blood flow, the actual thing that's causing the direction of flow, is pressure differences, and we've seen that. Remember, we identified you're going to get a lot of flow where you've got a lot of pressure difference. What's the logical order in which you put these? Highest to lowest pressure. So do it, have a quick chat, 10, 20, 30 seconds. Tell me where's the pressure going to be the highest? Let's identify that first. And if you're really smart, you look at the next slide. But you might as well talk about it before you do that. What do you reckon? Where's the highest?
Arteries.
I'm not allowed to assault my students.
I think it's aorta,
Yep,
followed by arteries,
yep,
followed by capillaries,
yep.
legs, and cava.
That means you're going to have, if you're going to go from high to low pressure, and that's the order of the system, then logically the pressures have got to follow in that order. Otherwise, it would be doing this. So. All right, Yossi, do you want to resolve the question for us?
You want me to talk through?
Oh, yeah, of course you can.
Okay. So you have here a graph that's showing you changing mean pressure within the blood vessel through different blood vessels. And what we can see here, obviously the aorta has the highest pressure, has a mean pressure of about 93 millimetres of mercury. And you think about that, the pressure generated in the ventricles is ejected from the heart straight into the aorta, so that pressure change is very small. Thing about pressure is fluid that travels down the pressure gradient. So if you want to move fluid around the body, you have high pressure at the starting point, low pressure at the end point. So the end point here is the vena cava. So we have next to no pressure. The lowest pressure is in the vena cava, and that helps us guide the flow around the body. So we go aorta, they're the largest diameter vessels. They're also the ones which are all that contain the highest volume of blood. And then the blood flows from the aorta to the arteries. The arteries are getting smaller in diameter. Then the blood flows into the arterioles. And what happens to pressure in the arterioles? Look at where the greatest fall in pressure is taking place. So from the aorta to the arteries, we have a small, according to this diagram, 13 millimetre mercury fall in pressure. And then from the arteries to the arteriole, we see a 20 millimetre, 40 millimetre fall in pressure. And that's because the arterioles are where there's all this resistance. There's a big change in diameter, big change in length as well. These are the vessels, the arterioles, which are controlling blood pressure, mean arterial pressure across the body.
All right. Who could tell me why that scale has those values on it? What's 93? It just seems like a random number to chuck in. Why not make it 100 or why put a 3 on the end of it? What's mean arterial pressure? All right, it's a defined value. Now, everybody knows, if someone watches a doctoring show on TV and they're taking blood pressure, what are the two values they usually give you? Systolic and diastolic, right? And what are those values commonly in the script of that TV show? 120/80, all right. So 93 is not an average of those two. 93 is a weighted average of those two. And it's weighted based on how much time the system sits in that particular phase. So how long it's in contraction, systole, as opposed to how long it's in relaxation, diastole. All right, and the approximation is to take your diastolic value, 80, and take 1/3 of the difference between diastolic and systolic. All right, so people are going, where's my calculator? I can see it, the eyes rolling. 120, 80, the difference there is 40. A third of 40 is roughly 13.33 recurring. 80 plus 13 is 93. And that is a good approximation of a weighted average of the systolic and diastolic, just based on time spent in those. Beautifully captured. All right, so here, everything about movement in the cardiovascular system and in the heart, and I've got to emphasise that, and in the heart is based on pressure difference. So direction is set by that. Have a look at the vena cava, the pressure down there. It's in single digits usually. But within the heart itself, right, it's even lower. So entering the atrium, right atrium, might be 2. Even lower in the ventricle. So the flow will continue to fill those vessels in diastole, right? So a lot of the fill is done just by pressure difference. Doesn't need contraction, etc. What happens is that valves will open or close based on those pressure differences, right? And that'll be an important consideration. What are we doing? Fluid, I can't read his writing all the time. Tracks down, pressure, beautiful. I think it's tracks. Travels. You're probably righter than me. Travels. All right, now let's look at velocity. Talk about flow. Flow at every part of the cardiovascular system, flow, right, is roughly 5 litres per minute. Every part. That's the output of cardiac output. 5 litres per minute. So when the heart expels blood, 5 litres per minute. But remember, it's going to have 60 or 70 beats. Each beat is going to expel about 70 mils of blood. So 70 times 70 is 4.9 litres. Right? 5 litres per minute, roughly. But every part of the cardiovascular system has to allow the movement of 5 litres per minute. Everywhere. And if you think it's coming out of the heart through a very narrow aorta and then branching into lots of capillary beds, right, the velocity changes, right? So where is the velocity travelling at its slowest in this? And I think I've got a question. You can probably go forward. Yep. So here, velocity. Sorry?
Pressure is flow divided by resistance. Pressure is flow divided by resistance.
Are you telling me or asking me? I'll believe you if you can derive that for us. And
No.
all right. Oh, how about that? Actually, it's at the highest velocity coming out of the aorta. What's the logic of having it slow in the capillaries? Fick's law, I hate it. I know you hate it now. Slow is good. Lots of time to get through to those thin areas. You don't want it thundering through your capillaries. You want it slowed down so you can facilitate exchange. All right, so if you look at your next diagram, I think it's a profile that says the reason that slows down is because you increase the surface area hugely. So if you look at this diagram, blood flow, 5 litres per minute, constant. Every section along the... So if I drew a line at the aorta and monitored and stood there and watched, 5 litres would pass by my eyes every minute. If I did that further down, arteries, I'd have to watch a lot more vessels, but collectively 5 litres per minute. Down to the capillaries, again, 5 litres per minute. But because it's spreading out over such a huge change in area, for the reason of feeding all the beds in the body, it slows down immensely. The analogy that's used to feed this is that it's like the comparison between a river that flows into a lake and then flows into a river again. Now, if you sat by, oh, this is so poetic, sit by the banks of the river, just chill, watch the water go by, right? It's probably thundering down that river, and then out in the lake, because it's diffused over, but at your single point, there'd be the same volume of water flowing per minute past you, right? But it's spread over such a huge surface area. So that's the analogy. Logically, based on the plumbing, that you've got to maintain flow. You can't have a backlog. If flow changes at any point in the cardiovascular system, things would bank up or void. You'd have areas where, oh, the bit's got ahead of me and I haven't caught up, etc. It's got to be continuous flow. That's supported by the elasticity, the smooth muscle and the elasticity of the blood vessels itself. And remember, I know, because actually I was standing in the back of the row last year when you were doing Windkessel principle. You're going, what were you doing in the back row? I'd just like to know what you know before so I can say, I saw you do that last year. You can't fool me this time. And I've actually got the video that you used. Right. Remember this little beauty. Yeah. Right. Cardiac output, 70 mil. Cardiac output, 70 mil. Flow is interrupted completely every time. Sucks. What a terrible system. Body would hate that. Right, so what do you do to change that? You create a reservoir, an elasticity, an ability to expand. All right, get on with it. We've already seen that. Right. Rubber. You was there somewhere. Right, balloon. Pretty much simple. Something that will expand. But watch the flow. Just watch the flow. Watch the flow. Watch the flow. The pump is still working. You did that deliberately, I'm sure. Anyway, you get there's a link there. Look at it yourself. That's how you can start to think about the actual architecture of your vessels in supporting these key features, like making sure that there's no backlog, that there is a pressure difference that's maintained that will create directionality, that we can have the ability to pull blood where we need to. So you have a lot of smooth muscle in your veins. Most of the blood sitting at rest, not that blood is resting, in resting condition, is actually in the venous system, because that system expands just to have a higher capacity. So how do we change that when we become more active? We just contract the smooth muscle in those veins and make that space smaller. So more of it comes back to the heart and goes into circulation. Now clearly it's not sitting there dormant, it just means there's a pool, it has a finite volume, which is of course constantly being pushed along, but as a total capacity. So the actual architecture can change here, and that change in architecture is really important. You're about to scribble something really meaningfully, and you've got probably 2 minutes to do it.
I don't know what you're referring to. This is probably projecting to what you might talk about next week.
Yep.
Which is, we've got to put them up on both document cameras because first thing is the big principal idea that David just mentioned was that everything that leaves the heart must circulate around the body. So if you have 5 litres of blood coming out of the heart, then you're going to move 5 litres of blood all the way around the body at the same time. So what I was alluding to here when we were thinking about that question about velocity through the vessels, we have this concept of pressure is equal to force times resistance. So if pressure is equal to force times resistance, you know that if the resistance in the If resistance in the capillaries is high because they've got a very small diameter, then the flow. Sorry, did I say force times resistance?
You did.
Pressure
Now you're confusing me.
Flow times resistance. Pressure is equal to flow times resistance. So if the resistance in the vessel is high, then the flow is going to go down to compensate for that. By the way, that statement, pressure is equal to flow times resistance, ends up with another equation you're going to learn for calculating mean arterial pressure, which is that mean arterial pressure is equal to cardiac output times total peripheral resistance. And then I'm going to jump back to the David take over.
No more equations. All right. So, and we will cover more to do with cardiac function next week. To summarise a lot of the things we've been talking about, very simple diagram here, but key things to remember are that the surface area and the architecture changes grossly as you move through the cardiovascular system. That the pump is the source of that pressure difference. The fact that we've got 93 as our mean arterial pressure, the weighted average of 120/80, etc., is because we pressurise the system through that contractility. Now we're going to do that in a coordinated fashion, so we've got blood moving through the right chambers at the right time. We'll talk about that next week. And we do that by having a series of connected cells that are electrically connected to each other, and they've got a little spark plug that keeps firing them off in a really good order, and they are good communicators. They talk to each other. But the reason we get flow in the direction we do is it's higher pressure here and drops progressively. You know it's going to drop progressively because it's going to interact with the walls of the vessels, and the longer it does that, the more the pressure drops. We just did the questions earlier about that. Long, tortuous bumping into walls, you will lose pressure. So we know at the end of it, it's going to be significantly reduced. It's going to change its velocity, right? So the flow rate will stay the same, so we still get the same amount of blood coming back that we sent out in the first place, but it's going to slow down at the points where it needs to slow down. So it can exchange. And it can pool in this venous system because it's a more flexible reservoir where we can leave it sitting there, and if we need it, we just constrict it and therefore increase the flow going back to the heart. And we can do that pretty quickly. So if we need more blood because we start more exercising and we need to up the rate, then we're going to increase the pumping. It's got to come from somewhere else. But if we draw a line through this whole thing, what's the rate of flow? At every point along this, it's 5 litres per minute at rest. And we can increase that, of course, in absolute numbers as we increase contractility. Now, what we're going to look at predominantly on Tuesday, I'll pick up any elements that we haven't touched on here, Tuesday morning. We're going to look at the excitation, the electrical system, the ECG, and the way it logically communicates with that. And then we'll talk about blood pressure. And blood pressure is really easy. I'll leave you with a little bit of what Yossi said, is that you control that whole system, the pressure of that system, by how hard you pump fluid out and how tightly you constrict those little valves at the end there, the resistance it's meeting. Right? 2 things, that's it. Put more blood into the system and the pressure will go up. Tighten the screws a bit more and the pressure will go up. 2 very simple tweaks. How the body does that is really interesting, so we'll talk about that. It's all right? It's all right? Nothing to be sorry about. Yeah.
I'm just a bit confused. You say the flow rate is the same, but the velocity is different.
Yep.
Right? So what's...
Well, what's velocity? One is volume per minute, and the other is distance travelled. Remember, velocity is velocity. How fast I go from A to B, closed volume.
So the same volume is going.
Same volume is going past you on the riverbed versus there. The lake versus the riverbed again. But the only way to do that is to go faster in the river than in the lake. It's the same about it. So which
my preferred analogy is you're driving down the southeastern arterial, 5 lanes of traffic, and you get to that tunnel, and they bottleneck. And the same amount of cars have to blow through at the same.
And they don't go at the same velocity, right? If they did, there'd be chaos.